the modern world, statistics power everything, from health decisions to social media algorithms. But where did it all begin? Join us as we learn the fascinating history of statistics across three major eras: the ancient civilization, the Age of Enlightenment, and the modern data revolution. Our story begins 1,000 years ago, long before probability or standard deviation statistics served one key purpose: record keeping. In ancient Egypt, scribes recorded crop fields and population counts to manage resources and taxation. In China, during the Han Dynasty, one of the earliest censuses in history recorded over 57 million people. In these civilizations, statistical tools were simple, like tally marks, knotted cords, and early abacuses. There were no equations or probabilities yet, just raw data for administration and governance. The Roman Empire, on the other hand, perfected the census around this time, using it to control their vast territories and military logistics.
Ovvero plebem dolentem, che subito patre.
But it wasn't called statistics yet. That term wouldn't appear until much later. For now, statistics meant statecraft.
As science flourished in the 1600s, the 1800s, so did the idea of measuring uncertainty. Welcome to the age of probability. In 1654, Blaise Pascal and Pierre de Fermat laid the foundation of probability theory while discussing gambling problems. Meanwhile, John Grant, often called the father of demography, analyzed London's death patterns or records to find patterns. Early descriptive statistics, tools and symbols emerged. The mean to describe averages, and the standard deviation to understand variability.
There are 15 children in a choir, and they're all different ages. If we list their ages horizontally, it's easier to notice any trends. The mean refers to the average. In this instance, we want to calculate the average age. If you add up all of their ages and divide by the total number of kids, this will give you the mean. The sum of their ages is 172, divided by 15 children in the group. This equals 11.46, with the 6 repeating, which will round up to 11.5. So the mean age is 11 and a half years old. Next up, the median refers to the middle value. In other words, if the data is organized from smallest to greatest or greatest to smallest, the value in the very middle of the list is the median, in this case, 12. The median is easier to pick out if you have an odd total like 15. But what if you have an even data set, and the two middle numbers are different? In that case, average the middle two numbers in order to find the median. It's okay if you end up with a decimal like 11.5. Last but not least, there's mode. Mode refers to the value that's repeated most often. Here we can see that 12 is repeated 5 times, making it the mode. If you had two values that were repeated an equal number of times, or two modes, this is called a bimodal data set.
In the 1800s, Carl Friedrich Gauss introduced the normal distribution, the famous bell curve that became the cornerstone of statistical thinking.
A statistician will, of course, point out that when data is distributed in this manner, the mean, which is also known as the average, is equal to the median as well as the mode, with the bell curve having exactly one mode. The bell curve is also, as can be noticed, symmetric. If you draw a vertical line at the mean, two mirror image halves result. Finally, if you know the mean, you know where the center of the bell curve or the proverbial top of the bell is, and if you know the standard deviation, you know how spread out the bell curve is. The larger the standard deviation is, the more spread out the bell curve will be.
These advances laid the groundwork for inferential statistics, drawing conclusions from data, not just describing it.
The 20th century saw an explosion in statistical thought, especially with the rise of computers. This is where tools such as Excel sheets help for easy research data analysis, and artificial intelligence come into play. Ronald Fisher, a giant in the 20th century statistics, introduced the analysis of variance, also known as ANOVA, and modern experimental design. Because of his contributions to the field, people gave him the name of Father of Statistics. And without him, statistics wouldn't be what it is today. Statistical hypothesis testing, pioneered by Jerzy Neyman and Egon Pearson, formalized how we test ideas using data. The symbols for null hypothesis and alternative hypothesis became fundamental to scientific research.
Now, as we conduct these tests, we're going to form two different hypotheses. The first is what's called the null hypothesis, and this is where we assume that there's no difference between the sample and the population, or no difference between the two samples that we compared. And in those cases, the p-value is going to be greater than 0.05. The alternative of that is we say that there is a difference. The sample and the population are different from each other, or the two samples are different from each other. And in those cases, the p-value is going to be less than 0.05. Now, in the cases where the p-value is greater than 0.05, we say we failed to reject the null hypothesis. We don't say that we accept the null hypothesis, we say we failed to reject it. Now, in the bottom scenario, where the p-value is less than 0.05, we say we reject the null hypothesis. So our two options are to fail to reject the null or to reject the null hypothesis.
During the World War II, statistics aided cryptography, quality control, and logistics, accelerating its importance in industry and defense. Then came the digital age, the age that we are in now. With computers, we could analyze massive data sets. Today, tools like Python, R, and Excel, plus the new artificial intelligence and machine learning, allows us to make sense of unimaginable amounts of data.
From tally marks to algorithms, statistics has transformed the way we understand our world. As data grows, so does our ability to ask and answer bigger questions. And that's the story of statistics, where it came from and where it's going.